Hi, everyone. This is Rob Gray from ASU and the Perception Action Podcast, back with another article review. Today, I wanted to review a really interesting article looking at player dynamics as a measure of skill. So, what we're talking about here's the paper published in Scientific Reports in Nature, very prestigious journal. So, congratulations. Nice to see this kind of work in there. So this is looking at soccer, football, dribbling skill, and they're going to look at whether a model of dynamics can predict. So what they're trying to do here is the overall goal of this paper is can we predict and measure and assess players' movements on the field solely based on a dynamical systems model, right? So solely based on information from the environment and the associated dynamics of that information and the action. Right. So we're going to see how far we can get in explaining how players move, where they go on the field, and so on, without having to infer any unmeasurable cognitive processes. Right. So we're not players. We're not have any strategy. They don't know what defense is being played. They don't know any play. They're not running. We're not referring what play they're running. Right. All we're doing is looking at the dynamics of their positioning relative to other players on the field, where the goal is, and so on. Right. So I'll get into it more, but that's the basic idea. How far can we get with a model that only measures that only looks at the observable, right? The information from the environment. That's basically what we're trying to do with any dynamical systems model. And this work was inspired a lot by something I talked about a few times on the podcast, Brett Fagan and Bill's model of steering or navigation, which came out in 2003. The idea of this model is you have an observer, right, trying to walk across. They're trying to get to a goal, right? So a goal offers affordance, right? A positive affordance, something you're trying to meet someone there, whatever it is, right? You're trying to get to that goal. So in the dynamical systems terms, the goal is an attractor, right? It's drawing you to. So this is different than a tractor we talk about in terms of technique, in terms of movement. This is a tractor in terms of drawing you towards it. So it's pulling you towards the goal, right? Over here, you also have an obstacle, right? So we have obstacles in the environment that offer, in Gibson's terms, a negative affordance, right? So remember, affordance is something, opportunity for action offered by something in environment for good or ill, right? So good is getting to your goal, ill is smashing into an obstacle, right? So in their model, the obstacle is repelling you, like it's pushing you away, right? And again, these are processes you can measure as simple dynamics in a dynamical systems. Right. So in their model, what they did was they had this repeller and the attractor, right? And they also had with multiple objects as well. And they looked at what route people took through different obstacles and goals, right? And obviously so here you have a person walking, their distance to the obstacle is much closer than to the goal, right? So the force of the repeller is going to be stronger than the force of the attraction. So in this case, the person's probably going to walk around the obstacle instead of trying to cut in front of it and taking the shortcut to the goal, right? Because of the relative dynamics, right? So that was the idea of their model. So kind of look at the repeller and the attractor. How can to what extent can we predict people's routes they take through cluttered environments, right? And this is what they got. They found they could predict the route people would take based on the relative positions of obstacles and goals, the repeller and attractor force, the dynamics, right? Without having to infer anything about their model, spatial model, or cognitive map of the world or anything like that. You get different routes solely based on the dynamics of the dynamical systems model, behavioral dynamics. Right. So that's the idea. That's what was inspired by this model. And anyone interested in kind of applying dynamical systems to the control of action, I would definitely encourage you to go back and look at Fagan and Warren's work. It's really quite remarkable. Okay. So that's the basic idea here. We're going to we're going to try to apply the same kind of model and some adding some other things to it to a soccer, right? So we're going to look at the player in the possession of the ball and the immediate defender, right? So we're going to look at those as a system, a dynamical system. We're going to treat the like a coupled system, also the position of the goal. Okay, we're going to focus on the player ball system and the delivering actions. Okay, the we're changing. Obviously, this is a dynamical system. We're changing the information that we get, and so on. Right. So we're going to get dynamics that emerge depending on the relative positions, angles of the player, the ball, the defender, and the goal. Right. So we're going to treat the ball and the dribbler as a couple dynamic systems. we expect dependent on the relationship to the other agents. The other thing they're going to do is within the model, they're going to give this, and this is going to be important for something later on. We'll see. They're going to create a parameter that represents the player's aggressiveness, right? How strong is the attractor to the goal, right? How much are they trying to get goal? And the repeller force of the defender, right? How willing are they to go out and challenge the defender, or how are they going to stay to the goal, right? And they model various versions of these, right? They just see how when they change this parameter, how it changes the outcomes, right? So we look at the location and the initial velocity of all these and the developed model. Okay. So without going into, I'm not going to, obviously there's a lot of math behind this and you can go in a lot of detail if you're interested. Here's the basic model. So you have the attacker with the ball, right? They're attracted to a goal. They have the defender that's repelling them, that's attracted to the attractor and the goal, and right. So the defender wants to get to the ball, but they also want to protect the goal, right? The route where the person is going to dribble the ball, the result is a result of all these inner forces, which is represented by a series of differential equations for the mathematically inclined. Okay. And so we have different parameters on the strength of the player's aggressiveness, how much are they trying to get to the goal, as I mentioned, and the resistance of the defender. Right. So that's the basic model. Attacker defender met as attractors, repulsors, or repellers. Right? That's the basic idea. Okay. What they did with this model, so they created this model to describe the movements of players on the field. They took data, they got data from the San Jose Earthquakes, a Major League Soccer team. They got player GPS tracking data, sampled at 25 hertz, and they used that data from basically it was from 4 players over 17 home games, right? So they looked at data from 4 players and they tried to see how well their model fit. Okay. And actually it fit quite well. So these are just, we can see there's 4 different plots showing different movements of the attacker defender depending on where they start relative to the net. So this model, again, I want to emphasize the importance of this. We can describe how people are moving, the resulting actions, without having to bring in anything about a play or their knowledge of defense or any kind of internal mental model that we can observe, right? We can observe distances and angles to the field, right? All of these, this is all in terms of observable metrics. Obviously, we have things that can vary the aggressiveness and things. We have parameters to it, but again, we're describing behavior. That's what the power of dynamical systems, right? We're describing behavior in terms of the observable, measurable things we see in front of us, not inferring something we can't measure. Okay, so that's kind of base. So the model they developed, they got a good fit to the data from the actual players, which was good. They then did this interesting thing where they developed what they call the dribbling score, right? So they looked at players' maneuvers at 2 different time points, right? And t and t equals 0 and t equals t capital T. And they looked to what extent when the player with the ball moved, did they decrease the angle to the goal and increase their separation from the defender. Obviously, the more you do that, the better, right? And they were determining, right? That's the goal. You're trying to get to the goal to create a scoring opportunity. So if you make a move that creates greater separation between your defender and you, and you get closer to the goal, then that's obviously a very skillful, good dribbling maneuver, right? So that's the basic idea of the score they created. Then they did something really interesting. What they did was so this score can go from 0 to 1. What they did was look at how that score changes based on those parameters in the model, right? So if they change the run. So the parameters in the model, remember, are the aggressiveness of the offender, the resistance of the defender, but there's also parameters I didn't mention, the top running speed of each of those, right? So what they did was they started with a point and they varied these and see how it changes the score and the trajectory, right? So they can do this kind of what's called a permutation method. And when you do this in modeling, where you vary some of the parameters and see the change in the outcome. So these aren't actually things they measure; they're varying the parameters to see how it changes, how the players would move as predicted by the model, and how it affects the score. And what they found is some really interesting individual differences, right? For the most part, obviously players with higher speed, right? You're going to have a higher score, right? In your maneuvers if you can move faster. But they found an interesting relationship between aggressiveness and speed, right? The top speed the players can generate. At some people, top speed obviously is the action capacity that you have to uh, put into this dribbling maneuver. For some top speed, it paid off to be aggressive. For some, it didn't, right? And that's kind of what they modeled in this model and they measured. So they basically, for each player, they can do these kind of measures and model predictions. And the interesting part about it, and I'll go to the next, right? So overall, what they found when they did this kind of permutation method is you got a higher score at when you had a higher top speed, right? So a 25 increase in top speed led to an 8% increase in that dribble score. Remember, the dribble score is how much your maneuver creates this separation. But there was very, very different amounts depending on the player, okay? So ability to run faster increases the likelihood of beating a defender one-on-one with the ball, right? That's not surprising. That's kind of intuition. But interestingly, the fact of changing the aggressiveness was different for the different players, right? For a couple of the players labeled A and C in the study, a 50% increase in aggressiveness led to positive increase in dribble score. Okay, whereas the other two players, increasing aggressiveness actually led to a decrease in their score, most likely because they didn't start with the same level of maximum speed, right? So what this can do, right, is so we can measure, we can look both identify things we need to work on with the different players, rather, working on their action capacity of their maximum running speed, or working on their calibration of their affordances, rather whether they should be less aggressive, more aggressive, right? So you could argue the players B and D should be less aggressive, right? Because their aggressiveness is not resulting in creating a positive score in terms of their dribbling maneuver, right? So that's kind of a really interesting finding. Again, we're explaining skill, identifying things we want to work on and practice through simple dynamics, right? I think this is a really, really neat approach. So these analyses demonstrate the possibility of using this model to quantify player attributes, right? Aggressiveness, um, resistance to play, right? And then making predictions about what we should, as I said, what we should work on and what players' strategy should use on the field. I think it's a really, really interesting approach. Um, we can also use it to destruct game plans, right? Where we know, if we know the players, we know where we're going to start an attack from on the field. We can predict the model what's going to create an opening, right? What's going to take a potential scoring opportunity. So it's a very ground up, bottom up model of soccer behavior. Again, in terms of dynamical systems. So I think it accomplishes quite a lot based on a few simple parameters, just like Brett and Bill's steering model. What they did is they showed, right, you can predict people's complex. You get, if you have lots of obstacles in a goal, people do these very complex paths through it, and they measured it. They showed it's highly predictable of actual people. They had people in a VR walking through these cluttered environments, and they got some of the model and the actual observed results are very, very similar. Again, without having to add any model in their head, right? They didn't have any model or goal like plan. They didn't route plan beforehand, right? We're simply explaining behavior by in the moment dynamics and the change in dynamics, the change in the information, dynamical, the distance, right? The angle and things like that. And, why? So this is a pure dynamical systems model of action that's predicting, I think, doing a very good job of this way, right? Where people always, I saw a comment on Twitter, like, why do people, and I had an episode on this if you're interested. Why do we combine ecological psychology and dynamical systems, right? They're a natural fit together because the problem with some of the dynamical systems models is the actual information source used in the model is not really a good fit of what people actually perceive, right? So, for example, distance, there's lots of research showing humans don't accurately perceive absolute distance. So having that as a parameter in the model here, it would be much better to quantify in terms of angles, optic flow, tau, all those things, right? So ecological psychology provides a better description of the information sources that when you connect it with dynamical systems, you get this magic happening. But again, I think this is a really, really interesting paper attempting to do something unique by looking simply at the dynamics of this interaction. Of course, they're going beyond this to look at multiple player. You can have multiple player interactions and different things. But I think this is a really interesting start. Okay, that's it for the perception action. That's it for today's episode. Cheers for now and keep them coupled.